Thank you for inviting me to this. It was great fun to be in Chicago. I've never been in Chicago before, so it's quite an experience to be here. It's quite unusual to find it colder indoors than outdoors, because in Stockholm it's the other way around. So when I was invited to give this talk, what happens when people invite me to give talks, I usually say no, and then I say maybe, and then I write a sort of title that I think looks okay, and I wrote a title and said I'd accepted this, and I tweeted this title.
Perhaps a bit louder.
And could you turn the volume up a tiny bit more, please? So I tweeted this title, Systems That Run Forever, Self-Heal and Scale, and immediately somebody tweeted back, well, that's impossible, you know, you can't. Can't. I mean, forever is actually quite a long time, so I'm not going to make systems that run forever. They just run for a few years, or you know, a few hundred years or something like that, but not forever, because the Earth's not going to be here forever anyway. So self-heal, that's pretty obvious. If they're going to run for a very long time, they're going to get bugs in them, so they're going to crash, and we need to fix them as they're going along, and we want to scale them up to sort of planetary-wise things. So that's the theme of this talk. And what I want to do is kind of set the scene for that, because I've been working with systems like that for quite a long time. And some parts of making systems like that is pretty difficult, and other parts are pretty easy. And so I want to kind of just give you some kind of feeling for the bits which I think are difficult and the bits that I think are easy, and how you go about doing that, and what's Erlang got to do with all of this. So the plan for this talk is I just sort of introduce the problem domain. It's this highly concurrent, highly connected world. Just talk about some algorithms and architectures, and then I just go into what I call 6 rules for making systems. I'm kind of not so interested. I mean, this might sound funny coming from me. I'm not really so interested in programming languages. I'm interested in solving problems. Erlang's one of those languages that was developed to solve a specific problem, and it turns out to be very good at solving that problem. Surprisingly, it's also good at solving other problems, but that's not by design, that's more by accident. And I'll talk about the reasons for that. Given that you've got those 6 rules, you could actually implement them in any language you like. If you constructed the language to have certain properties. You can bolt these properties on top of other language. They weren't explicitly constructed in that way, so you'll get the sort of feeling for it, but not the behavior that you get in Erlang. And I'll show you how they're programmed in Erlang. Right, so what's the problem domain? Well, I want you to think about, somehow we've got to go from this. That's a sequential program. That's all sequential programming languages look like that to me. It's just one sort of thing, and you've got to do everything in it. Right, that's all sequential programming, and here's Erlang, you see. So it doesn't look like that. It's a completely different world, you see. You're not talking about one process or one computation that's going to do everything. You're talking about thousands, possibly millions of computations that are going to do things. And they're all isolated. They're all doing their little things, and they're all talking to each other. So we have to understand this sort of world. I don't want to understand that other world. That other world is a very strange world. I mean, if you're programming things in the real world, they're parallel. I mean, the real world is parallel. With hundreds of people in this room, it would be extraordinarily difficult to try and describe that in a single I mean, how would I describe it? You're thinking that, and then I sort of interleave, and then you're thinking this, and then you're thinking that, and I go around you all, and then we get back to you. And how would you program that? I couldn't program that, but I could program it as, you know, 300 parallel processes. I always like to think of Erlang processes like little people, because we've all got private memory, and we all communicate by message passing. I've got my memory, you've got your memory, and I speak to you, and the words go. And this message passing channel is imperfect. You might not be listening when I speak, or you know, a jet might go by and obscure the noise, you don't hear it. So that's really how my little processes work. They've each got private memory. They just send messages to each other. We don't know if the messages get there or not. If you want to know if a message got there, you've got to send a message back. Then you'll know it got there. So we're not really making any big assumptions about how the world behaves. And this is actually how, I used to be a physicist. This is how a physicist would view the world. You know, there's no such thing as simultaneity. We don't know what's happening now. We know how it was at the time it takes a ray of light to go from A to B. And I don't see you now. I see how you were a picosecond earlier because of the time it takes light to get from me to you. And it's the same with software. When we send messages to each other, we don't actually know how they are now. We know how they were in the past. And we have to live with that. Well, we can't change the laws of physics. We have to live with that. So this world has got lots and lots of computers. Lots is a sort of rather vague term, but it could be anything from, well, I wouldn't call 2 lots, but it's certainly more than one. Probably lots starts at about 10 and goes up to a few tens of thousands, possibly millions of computers. We don't actually know how to program millions of computers in Erlang at the moment because we haven't got millions of computers, but there are research projects who are figuring out how to do that, actually. The million-core CPU sort of projects are sort of going on to the research horizon now. Of course, if you've got this world with lots of computers, they're all executing things in parallel, and it's distributed. It's concurrent because they're all running at the same time, and faults are going to happen. And so it's not a question of saying, well, let's use type systems or let's use something so that no faults can occur. It's more the case that faults are going to occur, and then you're going to have to detect them and do something about it. You're going to have to worry about consistency, or rather the lack of consistency. I mean, if you've got thousands of computers, it's just kind of unrealistic to think you can put it into a consistent state. So you're going to have to live with inconsistency. And if you want it to run forever, you're going to have to change the code in it as it's executing. I mean, you just cannot, there's no such thing as an atomic upgrade. Stop it, change the code, restart it if it is every single computer on the planet. It's just not going to work. So you're going to have this notion of things sort of partially upgrading themselves, and an upgrade to take time, and of living with different versions at the same time. So one of the things, actually the primary thing that Erlang was designed to do was to do fault-tolerant computation. So let's just think about that for a moment. So there's this kind of world. There's really 2 ways to design things. You can either sort of start with small things and scale them up, or you could start with big things and scale them down and see if you get it the same way. So suppose you're building a system and you want it to be, say you want to build a system for like 10,000 people to use simultaneously. One way of doing it would be to start with the system, design it for 10 people and test it like that, and scale it up to 10,000. The other way would be to design it for like 100 million people. I mean, do the design for that and then scale it down to 10,000. And you might not get at the same architecture. You might get a completely different architecture. In fact, you would get a different architecture. And I think in general it's a really bad idea to start at a design that works for 10 or 100 things and scale it up. It's better to start with an architecture that you know will work for a few trillion things and scale it down. It will actually be less efficient when you've got your 10,000 than the one you scaled up, but you'll know that you'll be able to scale it up later. So it's good. So rather than ask how do we get to 5 nines, I'd really like, let's make it more interesting. Let's start at 9,999 nines reliability and scale it down. Okay. So let's make a system that's got 9,999 reliability. Well, that's easy. Well, it's not quite easy. There's a tricky bit, right? So, well, that's really easy because if things are independent, this is just probabilities. You see, if the probability that one thing fails is 10 to the minus 3, you just get 3,333 independent machines and run them all in parallel. And the probability they all fail at the same time is 10 to the minus 9999. So you've got your 4 9, oh, it's not 4 nines reliability, it's 9,999's reliability. That's pretty easy. Okay, so the difficult bit is making them independent. Right. So, oh, and does this work? Yeah, I've just put in a few slides to show that well, we believe this sort of technology works. This is this is what I do, right, when I'm not here. I work for Ericsson, and this thing here is a connection, but this stuff down here, this is your 4G, LTE, wideband CDMA, 3G out here. And this stiff stuff over there, IP network, that's internet. Right. And we put a box, so let me The software abstraction of that is this. Okay? Well, software people, they do bubbles and arrows and things, you see. So this is millions of smartphones, and that's Erlang, and that's the internet. And that box in the middle, that connects smartphones to internet. Now, it actually connects about half the smartphone traffic in the world. Right, so if you've got a smartphone, and if you're using data traffic, then there's about a 50% chance you're going through an Erlang thing. If the base stations are programmed, if you've purchased your base stations from Ericsson, okay. If you've purchased them from our competitors, then they won't be in Erlang, they'll be in C++ or something like that. So it's about half the world's smartphone traffic is going through these things. And we built a thing here. This is Ericsson. I've just sort of taken some stuff. That's the, I showed you the first picture, that was the architect. The second one's the software abstraction. This is the sales abstraction, which I show to customers. That thing is a box. It's a big sort of box. It's not really very exciting, actually. But it's one of those boxes, right? We don't sell many of them, actually. Has got the goals are 6 nines reliability and 18 million simultaneous connected subscribers and low power consumption per person. That's all programmed in Erlang and works quite nicely. Thank you very much. So this is pretty similar to internet high availability. There you want sort of thousands to millions of users, kind of soft real time, upgrade them as they go along. You don't really stop these systems. I mean, Google doesn't sort of go offline to do code upgrade at midnight. There isn't really a midnight, because when it's midnight here, it's not midnight in Sweden and so on. So there's not really a midnight when you, perhaps they stop it at midnight in America and change all the code and restart it. And that's what the banks do. They turn them off at 4 o'clock in the morning and leave them off. It takes about an hour or something, and then they come back online again. And well, we don't do that in telephony. Google don't do it. We want to make these things very scalable. Right. So I was kind of looking for some. Distributed programming is, in a sense, hard. It's also difficult. It's also easy. But I searched on the internet a little bit. I was just searching why distributed programming is hard. I found this blog, and I sort of, oh, that's right. I don't know who this guy is, but he'd written a blog. He put down 5 reasons why distributed programming was hard. So I wrote them down here. I thought, yeah, I agreed with that. It's difficulty in identifying and dealing with failures. Well, that's what he wrote in his blog. I disagree with that, actually. I think that bit's quite easy, and I'll tell you why. Point 2, achieving consistency in data across processes is difficult. And I'm going to go into that in a little bit of detail, just to give you some kind of feeling for why I think it's difficult. These big systems, they are not homogeneous. We don't build systems in one language. Even if I'd like you to build the whole system in Erlang, you're not going to do it. You're going to build it with several different languages and try and connect them together. And testing them is pretty difficult, because they're not kind of reproducible. You can't put them in the same state every time. And often, these big distributed systems require an awful lot of special purpose hardware and kit. I mean, in order to test some of the software we were writing, you had to book a test facility, and you could get like 2 days in 3 weeks. And that wasn't enough. You go into a room half this size full of equipment and say, okay, here's your test facility. And you haven't a clue what to do. So you need a whole lot of little chaps who run around, and you tell them what you want, and you've got to rig it. And that's what actually makes tests, continuous development, all this continuous stuff. Well, you can't do it if you need a whole pile of hardware that's really difficult and really expensive, and you can go into it, move in for 2 days, then move out again. You can't just sort of rerun them every time you commit your program. So it is actually difficult to test. And so the technologies in distributed systems are not easy to understand. I'll give you some examples of that. Not just to sort of frighten you off a little bit, but they are kind of tricky. So I'm going to look at data. So highly available data. I'm going to say data is sacred and computation isn't. You really need to look after your data, make sure you never lose it. Computation, that's just stuff that transforms data. So if your program crashes, just rerun it or something like that. That's not a problem. You can perform the computation anywhere, provided you can get hold of the data. So I'm going to look just at a sub-problem, and that's how to make highly available data. Okay, so let's look at the where is my data problem. I like this. So imagine you've got 10 million, that's my thing, you've got 10 million computers, and you've put your data, Joe's data is on 3 or 4 of them. So the first question you want to ask is, well, in order to access my data, I'd need to know which computer I've put my data on. How could I find that out? Right. Oh, that's pretty easy. We know how to do that. So most of the algorithms, this is one of my favorite algorithms, the chord algorithm. That tells you how to put data, how to find the computer that all my data's on, if I've got millions of computers. So for those of you who don't know it, I'll just go through it rapidly. What you do is you map the IP addresses, or the hash of the IP addresses and the hash of the keys into the same namespace. Okay, so I'll give you a simple example of this and use MD5 as the hashing function. So suppose you've got 3 machines, well, more than 3, I've got several machines there, but the first 3 machines have got IP addresses 235, 23, 34, 12, and so on. So the first thing I can do is compute a hash, sorry, an MD5 checksum of those, and I did that there. And then sort those MD5 checksums. Okay, so the next list here, that's the sorted MD5 checksums. And then if I've got a particular data, suppose I've got a key, something like this mail number 2. So if I hash that into an MD5 checksum, I also get an MD5 checksum. If you compare that with this list here, okay, and you say, well, that occurs in the 3rd position in this list here. Now, the 3rd position, well, between the second, you see the first 2 entries, the hash of 09934, that's machine S2, because I've sorted them. And the second hash is machine S3, and so on. So this hash here occurs between the 2nd and 3rd entries in that row. And that says, it's just a convention, I'll store that data on the machine with the hash that's the first value that's lower than that. Okay, so I'm going to store that on the machine S3. Okay, so by hashing key values into the same namespace as the hash of the IP addresses, we can figure out which of these machines to store it on. And if you want a replica, well, you hash it again, so you get 2 machines, and store the second one on the second machine. Of course, it might hash to the same machine, so if it went to the same machine, just do it again. And that's the chord algorithm, right? And it's actually the basis of all, well, not all distributed hash tables, but most of them work like that. So it's actually quite easy to understand. Very pretty algorithm. Okay, so let's look at these replicas. So you can find the data. That's not a problem. That's pretty easy. But I'm trying to replicate data in case the machines crash. And so I'm storing in 2 or more places. Now life becomes a bit more difficult. So your first thing is, okay, the first thought that people have about replicas is, I know what we'll do. We'll keep an odd number of copies, and we'll vote. You know, you'll send out, like, say, keep 5 copies, and you send them out. And when 3 of the machines have said, yeah, we agree, then you say, yeah, it's okay. What about the 2 that didn't agree? We'll forget about them for a moment. We'll forget about them for the moment, is going to come and bite us in the bottom, I think, later. But never mind, it sort of looks okay, the majority wins. And what about the time? Oh, that's brilliant. Look at that. We've got some master machine here, and it's broadcast to 5 machines, and then it gets 5 answers. But all this takes place in parallel. Okay, so in wave 1, you send out 5 messages, and then you get 5 replies. That's great. Fantastic. As soon as you've got more than 3 replies, you can say, yeah, that's great. So you can have 17 replicas, or you can have 9,999 replicas and wait until more than half of them are replied, and you're okay. Isn't that easy? You see, it's linear time. Doesn't matter how many replicas. Easy to find the machine. Everything's simple. Yeah. Now, at this point, you're thinking, distributed data is really easy. Right. Right. So making replicas is pretty easy, isn't it? Right. So if we can make 9,999 replicas, well, it's going to be easy. So I just thought, let's look at two. I'm a bit sort of, I like to understand things. So I think, well, I don't really understand 9,999. Let's try and understand what's involved in making two replicas, because that's a much easier problem. Right. So here's how we've got two replicas. You see. Let's suppose we've got a master machine A and a replica machine B, and we send a message to it. Set X is 10. Sends a message to the B machine. Set X is 10. And you get an ACK from the B machine, and you get an ACK from the A machine. So at this stage, what we know about the system is asymmetric, right? Because A knows that X is replicated on B. But B does not know that X is replicated on A, because somebody might have told A to change the value, and it hasn't yet got a signal, right? So it's asymmetric, and that's going to be very nasty. Right, so let's see. So what happens if everything, let's suppose we've got well, it's not going to kind of work like that, because you've got two machines, A and B, and you've got a client. They can't talk to A all the time, because they don't know where A is. So normally you have a sort of load balancer or a master machine that knows where A and B is. And so the client actually talks to the master machine who knows where A and B are, and it always talks to A. So this is what happens if everything works. So the user sends a message to the manager. That knows where A is. The manager is the program that's executing the chord algorithm, okay? So it sends a message to A, set A, and you get all these ACKs back, and it all works beautifully. And there we go. So we set X equal to 10, and then we set it equal to 20, and everything's fine. Right. So, hang on, what happens if A crashes? And then the client asks for the value of X. Well, up to this point, so it's crashed at this point. So the user set X equal to 10, and some stuff's worked here, and that's fine. Then he set X equal to 20, and some stuff's worked. And then this process crashes at this point here. So the master here knows that A has crashed, and now somebody asks for X. Okay, well, the master knows that A has crashed, so he asks B. And he gets back a value of B that's 10. So what can he reply? Oh dear, this is a sort of unsafe value of X. I know it's 10, but it might not be. Right? Because you see, it's actually 20, I mean, it's been 20 here. But he can't ask A because A is dead. But he knows that A's died, and he knows that B, so, oh dear. So we've got this unsafe value of X. Now, what do you want in your program? Oh, you do a get and put into a database. And you say, yeah, what's the value of X? Yeah, it's 10. What's the value of X? 10. Oh, oops, sorry. What's the value of X? Well, I think it might be 10. So programmers don't want to know this. And so other programmers put abstractions like two-phase commit. And so even though you're getting it, well, I'm unsure about this, really, they say, oh, I'm sure, it's 10, you know? Right. So now we have to, what happens if the master, now, well, wait a moment, look, hang on. So this was kind of tricky. You see, here's the A has died, but the master process hasn't died, it's still living. And then it's beginning to get a tiny bit complicated now. So now we say, oh, well, what happens if the master process itself dies? Right. This is you don't want to know stuff. Well, I'm going to tell you a little bit, right? Life gets a tad tricky, okay? So have any of you heard of the Paxos algorithm? Right. So you know life is a tad tricky because of the Paxos. So the Paxos algorithm is distributed leadership election. It's the problem you have a leader just dies, and then you've got to, in a distributed way, figure out who a new leader is, and you kind of vote and take the majority. But as you're voting, you might lose messages and they might die. So if you look it up, say, on the Wikipedia or something, you'll find these signal diagrams. They look pretty much like the ones I've been drawing, only there's about 15 to 20 of them that look like that. That's one of the simpler ones that will fit on the slide. So in making this lecture, I did a little bit of research, and I found a quote I rather like, because it was from a paper. The paper was called In Search of an Understandable Consensus Algorithm. I like the word sort of understandable consensus algorithm. And to read you a bit, it says, unfortunately, Paxos has two significant drawbacks. The first drawback is that Paxos is exceptionally difficult to understand. The full explanation is notoriously opaque. Few people succeed in understanding it, and only with great effort. As a result, there have been several attempts to explain it. These explanations focus on a single-degree Paxos. They are still challenging and leave the reader with not enough information to build a practical system. In an informal survey of attendees at something or other, we found few people who are comfortable with Paxos, even among seasoned researchers. We struggled with Paxos ourselves. We were not able to understand the original paper. That's the one Paxos simply explained, you know, so... until several simplified explanations in designing our own alternative protocols. And look who wrote it. Well, one of the authors is John Oosterhout. Do you remember TCL? Very nice language. So John Oosterhout, I mean, he's not a dumb guy, right? He designs programming languages. And programming language designers sort of a bit anal about understanding stuff. So they try and figure out how it works. So if John Oosterhout says he couldn't understand it, and it's kind of tricky stuff, that's good enough for me, you know. I mean, it is actually. So that's the bad news. Okay, so what's the good news? Well, the good news is that it's been solved in the Erlang, I'm going to say quotes, in the Erlang libraries, you see. So there's a gen leader thing in the Erlang libraries. That itself is a sort of, this problem was so difficult that we had a research project to do this, and the research bit of it was the project bit was to write the leadership election algorithm, and the research bit was to prove that it was correct, right? And they proved it was correct. And it ran for several years. And then, I can't remember when it first was, but then they got a bug report that the leadership election was actually electing two different leaders, and it was reproducible. And this was a bit of a problem because it had actually been proved to be correct. So we went back to the people who proved it, and they said, oh, well, we had to make a few simplifying assumptions in order to do the proof. So it's believed to be correct at the moment. And if you don't want our libraries, there are things like REAC, which is a database, which implement these kind of algorithms, and they actually give you fine... REAC actually is quite nice because instead of sending this... normally things hide the voting structure. So if you've got 5 replicas and you really wanted to be sure that it really worked, you'd really like to maybe know that you've got 5 commits, not 3. Most databases and things don't allow you to do this. REAC has this kind of layer of fine control where you can sort of say, well, I really do actually want to know exactly what's going on, and you can sort of go in at different levels, which is very nice. So this was just a little sort of introduction to some of the problems you get in distributed programming. I don't think that you need a lot of complicated, fancy algorithms to do distributed programming. But certain ones, like replicating data, you do need, and you certainly don't want to implement them yourself. So you really want kind of rock-solid industrial quality implementations of that stuff, and don't try and build it yourself, unless you're a research group and want to spend 10 years doing it before you know, if you just want to build something. Take these libraries and use them. You don't actually need that many. There's libraries like REAC, AMQP, the RabbitMQ, is a persistent message queue. Think about it, you can implement a heck of a lot of things just using persistent message queues, and it's just nice to know that somebody else has done all that work of putting that into the library. These are the libraries you want. You don't need libraries for web services. Any fool can... No, but look, any fool can write them, right? But this stuff is difficult. Okay? Right, so let's look at some rules for... These are sort of properties that you need if you want to make fault-tolerant systems. And you know when people... I don't like, you know, slides with... Well, I've got slides with bullets, but, you know, trouble with slides with bullets is all the bullet points are the same size, so you don't know which is most important. So really, I'd like a patent, you know. Big bullets mean it's important, small bullets mean it's not important. So if you put on a bulleted list all the things that are important, the biggest bullet of all is isolation. Processes must, or computations must be isolated from each other. That means that one process can't crash another one. It doesn't really matter if my process is, suppose I've proved my process correct and tested it, and it's wonderful, and then some other bloody idiot comes along and just crashes it, pulls the plug out of the computer. I've proved your program to be correct. I've built a fault-tolerant system. I've built it on one computer, and some guy comes along and says, oh yeah, and pulls out the plug. It's not fault-tolerant, is it? So this isolation property is very important. I know, because this computer is isolated, I know that if I just walk into the... Can I walk into the audience? Do I have a volunteer who will give me one of these beautiful computers and I'll smash it and show that my slides are still working? Do we have a volunteer? Or do you believe me? Sir, can I take your computer to smash it? Do I need to smash your computer, or do you believe me? You believe me, right, that's great. Take the challenge, I'd be really surprised if I went and smashed a computer here and the slideshow stopped, or if somebody smashed a computer in Sweden and it stopped. That's isolation. Okay. And we want that for our software. Right. So once you've got isolation, what does it give you? What do you get for isolation? You get a heck of a lot of nice things. You get fault tolerance, because if I just smash this machine, it's not going to cause what's going on in these other machines to stop. It gives you scalability, because if I have organized my computation so that it will run on one machine, isolated from another, then if I want twice the power or 10 times the power, just get 10 computers and put 10 of these things. So designing my system for isolation, making sure the bits are isolated, gives me scalability. And it gives me reliability. Okay, it's pretty much the same as fault tolerance. It also gives me testability. Because I've isolated it, I can test it in isolation. If it's not isolated, if it's lots of bits all glued together, how the heck do you test it? The more I can isolate the bits, the better I can test them. It gives me comprehensibility, because this act of isolation is taking things into smaller components, talking to them through protocols. That gives me the ability to test them. Okay. And it gives me the ability to upgrade the code in them. Because once I've isolated all of these, I can now go around the room turning off one at a time, changing the code in it, putting it back online again, then going to the next one. So I'm going to get all these things for free, provided I have made an architecture with isolated components. Okay, so once they are isolated, the next property I need is concurrency. Can I describe a computation in terms of concurrent processes? Because if I've now isolated them, they are concurrent. I can't do anything about that. So does my system, I'm not talking about programming, is it an operating system, a programming language, does it enable the description of concurrency in a sort of rather natural sort of way? Okay. Well, why do I want concurrency? Well, world just happens to be concurrent and parallel, just go out in the street. If you don't believe it's concurrent, just walk over the street outside there, when all the cars are whizzing by. It is, all these cars are sort of zooming around. All this stuff is happening. If you try and describe that in a sequential process, how would you do it? I don't know how. You can't. So, the world actually is concurrent. So let's try and describe it in a concurrent language, or a concurrent way. That doesn't mean to say it will execute in parallel. It means the description is as of a set of parallel concurrent activities. You see, I can't, if I run it on a sequential processor, a one-core computer, it'll never be parallel. It will be concurrent, however. I get the illusion of parallelism by interleaving the CPU. If I've got like 1,000 computers, if I've got a 10-core CPU, I can run 10 parallel processors on it. I can't run 11. I can run 1 million concurrent processors on it, interleaving onto the 10 processors. We have to distinguish these two ideas. We also need, at least 2 computers to make a non-stop system. I always thought that was obvious until, you see, I've been working for this so long, I didn't realize that people thought, oh, you actually, you can make a fault-tolerant system on one machine. I said, well, what happens if you smash the whole machine? They go, oh, I didn't think of that. So, So Ericsson, you see, we do this sort of. Mike Williams, who worked with me for years and co-developer of Erlang, said Ericsson built military systems, and they had a bit that built things for generals and people with funny hats on, so this general came in and said, we've got the talk about, 2 machines, you knock one out, it carries on the other one, and he was very pleased about this, because he said to Mike, I always wondered what would happen if a nuke hit one of the exchanges. So you're telling me if a nuke hits one exchange, it will still carry on going. Well, sort of Mike's mental model of this was like 2 computers sort of in the same building, stood up with a wire in between and duplicated power supply. So you didn't have the sort of mental model of there being like 400 kilometers between them to guard from nuclear weapons and things. But a little bit of thought said, yes, it would work. So the general was happy. Yeah, so, concurrency, it kind of goes together with this distribution. If it's distributed, it is concurrent. You've got to live with it. You can't. So here's a funny thing, you see. If you want to write fault-tolerant software, you have to do concurrent and distributed programming, whether you like it or not. It's not an alternative not to understand distributed programming if you want to build fault-tolerant systems. Because you do need 2 computers. They are in parallel. They are distributed. You can't get away from that. Right. Next thing you want to do is detect failures. Machines are going to die. So if you can't detect the fact that they've died, you won't be able to correct any errors that occur when they die. Pretty obvious. Failure detection. Right. So, yeah, if you can't detect a failure, you can't fix it. And this has to work it's got to work sort of transparently across machine boundaries. And that implies actually non-shared data structures. You've got you can't have like dangling pointers over machine boundaries. You can't sort of lazily transfer data and have half the data on one machine and half the data on another machine, because if one of the machines crashes, you've lost half your data. Okay, so it sort of implies this kind of pure message passing where you copy everything. The real reason for that is fault tolerance. It's not to do with anything else. It's not to do with efficiency or anything. I mean, I always thought, first of all, you make systems right. That means fault tolerant, and then you make them fast, you see. The consequence of making them right is you can't have lazy data structures with dangling pointers over machines. You have to copy everything, otherwise you can't make it fault tolerant. And actually, I also want it to be asynchronous message passing, because you can't do synchronous message. And the world is asynchronous. Light sort of moves from A to B and takes a certain amount of time, and you can't change the laws of physics. Right. We build fault-tolerant things into little, in Erlang, we build them into trees of things that sort of watch each other. And these work transparently over machine boundaries. And this is a kind of logical picture. They could all be processes on the same machine, or they could be processes on different machines. It doesn't really matter. You need also fault identification. It's not enough to know that something's crashed. You really want to know why it's crashed. At the lowest level, Erlang gives you a kind of simple, it crashed because you divided by 0, or it crashed because something was wrong. But you can tune that. You could send a lot of entire databases with you when it crashes. You send the entire state of the system when it crashes if you want to. I said that. And then you want live code upgrade. Pretty obvious. Won't really say much about that. I did say something about it. You want 0 downtime. Once you've started, there's no stop button on your software. You press the start button. That's it. Go home. It'll go forever. And you want stable storage. I mentioned stable. That's this, store my data. That's one of the tricky things to do. That's not a property of a programming language. It's a property of programming language and algorithms and operating systems and all sorts of stuff. But it's kind of pretty good now. This is kind of off-the-shelf stuff. It's quite nice if you've got proper storage. You don't need backup anymore. Well, what the hell have got backup for? You don't need backup. Backup's something you want in case your machine crashes. But if you've never crashes, you don't need backup, do you? So remove that. You do need snapshots, because you overwrite your data, but you don't need backups. You need crash reports and things like that. When it crashes, it's nice. It's nice if you can come back later and say, oh, well, despite it's all crashed, it's still in the storage why it crashed when we start it again. I just wrote a quick few quotes from various people about how you build fault-tolerant systems and things like that. Well, Jim Gray is actually wrote this paper, Why Computers Stop and What Can Be Done About It. Does anybody of you remember the tandem computer? Oh, excellent, good. Not the only one with grey hairs. Erlang is, in one sense, the tandem computer in software. Its architecture is very much like the tandem, because I read Jim Gray's report and I mailed him and said, Erlang, he'd postulated if you were to do all this in software, it worked pretty much like the hardware, he said. And I said, yeah, well, we've done it in software and it does work pretty much like the hardware. And he mailed back and said, yeah, I know. It would do. He also said, welcome to the Church of Concurrency, he said in his mail, which I thought was rather nice. And he said, in order to, I just highlighted a bit, see, process achieves fault containment by sharing no state with other processes. Its only contact with other processes is via messages carried by the kernel messaging system. So that was the only way that data could be exchanged in tandem. And he said, the key to software fault tolerance is to hierarchically decompose large systems into modules, each module being a unit of service and a unit of failure. And the failure of the module should not propagate beyond the module. This seems to me straightforward. Actually, I haven't got it on this slide, but Postel's law of making matters worse law, sort of be tolerant in what you accept. And, this is an absolute nightmare because, you send, what are you supposed to do? You define a protocol and then you send a message that is in violation of the protocol and you say, oh, well, that's okay, we'll let it in anyway. It's horrible, you shouldn't do that. You crash immediately, no. And then Gray, a guy called Gray, it's pretty much the same. Transaction mechanism in process per software modularity through process and message, same sort of idea. And there's a notion of fail fast. The process approach to fault isolation advocates that process software should be fail fast, that either a function should function correctly or should detect the fault and stop operating. As soon as you've got a fault, you stop. Don't make matters worse by continuing. Right. And then fail early. This is somebody else. A fault in a software system can cause one or more errors. The latency time is the interval between the existence of the fault and the occurrence of the error can be very high, which complicates the backward analysis of the error. This is a paper from sort of business systems. If error occurs now and you carry on and carry on and carry on and carry on and then you get the symptom, it's very difficult going backwards to find out where it occurred. Right. And who we got? Oh, Alan Kay. This is a nice mail he sent, a reminder that I took some pains at the last, oops, I should extend this. Small talk. It's not only about its syntax and class library, it is not even about classes. I'm sorry that I, a long time ago, coined the term objects for this topic because it gets many people to focus on the lesser idea. The big idea is messaging. So the big idea of object-oriented programming is messaging. It's not objects, and it's not classes, and it's not methods, it's not how they're organized. That's abstract data types. The big idea in object-oriented programming is messaging and polymorphic messaging. Right. And of course, all this is in Erlang. And Schneider, it's the same sort of stuff. Anyway, I summed all this up into Joe's quote, let it crash. Right, so just let your software crash. Now, crashing is a big deal in sequential programming languages because you've only got one process. So if you crash, you're screwed. Right. Well, what else do you do? Okay. So wait a minute. There's a corollary to this. All sequential programming languages get error handling wrong. Every single one. Doesn't matter what they are. Doesn't matter if they're Java, Haskell, Smalltalk, all of them. They're all wrong because they all have this notion of one sequential computation. You've got to do everything inside it, so you have to keep it alive no matter what happens. So what happens when you're writing a program and you get to the point in the program where you cannot return a value to something, where it doesn't make any sense to continue because you figured out that what's going wrong didn't agree with what should be? You've got a violation of your internal logic. What can you do? You have no alternative but to crash. You can't logically continue. There is no way you can. Suppose you've got a factorial, suppose you've got a divide by x, and x turns out to be 0. What do? You can't continue in it. You can't, throw not a number or something. Come on, just crash, for goodness sake. But you see, it's not a problem with this airline, because you've got millions of processors all watching it. Who cares if a few processes crashed? Oh, dear. Right, so there were 6 rules. So how are we going to program them? Well, what's Erlang? Going to program in Erlang. So Erlang's a functional program. Well, it's kind of 3 things. Which it's like, this will come, when you unwrap the parcel, you find 3 things inside it. It's a functional programming language. Probably in respect to Haskell, it shouldn't be a big F, it should be a sort of little f. It's got a few non-functional things in for pragmatic reasons. You can program in a very functional way if you want to, but you can also, don't have to. It's a set of design principles. They go under the name of OTP, which is a very self-evident name, middleware, open telecoms platform. Oh, well, we're not doing telecoms, it's useless, right? So, but that's all about fault tolerance and setting up these things. And it's a virtual machine called the Beam. B stands for, it was designed by Bogdan Hausman, which is what's a B in it. So it's Bogdan's abstract machine, but then Bogdan left and Björn took over. So Björn Gustafsson now supports it, and so it's Bogdan and Björn's Erlang abstract machine. Right, so how do we program the 6 things? Well, we could use libraries, or we could use things in Erlang that were designed to do that. Okay, so what about okay, let's go through the isolation rule. Well, Erlang processes just are isolated. One process cannot damage another by accident. It could damage it deliberately. It can send an exit signal to it, but that's not accidental. You shouldn't be. Perhaps I should say you can't accidentally damage other things, and also you can't really kill it. It might set a flag saying, "No, you're not allowed to kill me." But there is a special message that you can actually kill processes, even if they've said you're not allowed to kill them. And an Erlang node can have millions of processes. They take about 300 bytes per process. You get 3 processes per kilobyte. So you get 3,000 processes per megabyte and 3 million processes per gigabyte. But that's before they're doing anything. So, with a few gigabytes of memory, you can run up, a few tens of millions of processes without any problems. Just try it at home. It's quite easy. They've got no shared memory. And they're very lightweight. They're much lighter weight than threads. Operating system threads are very, very, very heavy compared to Erlang processes. And threads are evil anyway because they share resources. So, threads don't obey this. Here's the crazy thing. You've got nice things in operating systems which are actually isolated. So one process can't fuck up another process's internal data structures. But threads are evil. Because what's the difference between a thread and a process? Oh, the threads can fuck up each other's internal data structures. So they're absolutely the things you don't want to program with. Right. Concurrency, well, Erlang processes are concurrent. Yeah, they all run in parallel, in theory. And actually, on a multi-core, they really do run in parallel. But you can't get more parallelism out than the number of cores. So you've got a 4-core machine. You're not actually running more than 4 of these processes at a time, and they're scheduled and they're preemptively scheduled. And they do within a thread. They block for I/O, but they're non-blocking with respect to other processes. So a process will go like read, write, read. It'll go read, write, read, write, read, write, read, and when it says read, it waits, but it doesn't affect anybody else. So they all carry on. So it's not one of these funny languages that say, issue a read request, on read complete, call this function over there somewhere. Woo-hoo, bye. And then and then the read complete goes. It goes right, 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 read. Oh, on read complete, go over there and do something. You know, it's not like that. So it's actually easy to understand. And it's actually just 3 little things in Erlang. You know, spawn creates a parallel process, PID bang message sends a message, and receive. It's pattern oriented syntax. What it actually does, it doesn't actually send a message to the process. Each process has a mailbox. Okay, so you send to the mailbox. So this is just like regular mailboxes. PID bang message tells the VM, which is a postman, says, deliver this message to this guy. So it doesn't need to know where it is. It's location transparent. This will find its way over the network. It's just like a letter. If I put Nackagatan 27 on a thing and pop it in the post, it'll turn up in my mailbox in Sweden. Okay, so that's the same as in Erlang. Once you know this address, PID bang messages, send it off, and it'll end up in the mailbox. And this receive operation says, hey, just go look in the mailbox and see if you've got any of these mails. It just takes them out. Any other mails that are there, it won't lift them out. So there's a pattern matching operation that lifts things out of the mailbox. Right, that's the concurrency bit. The failure detection bit just says, well, you can set up a link between these processes. If the process dies, it'll send you a message and it'll end up in your mailbox. That's all it says. Actually, 2 types of messages. Actually, the technical called signals. What really happens is, if you don't do anything and you link to another process and it dies, and if the reason it dies is because of an error, not a normal death, you yourself die and you send out messages to the processes you're linked to. And the reason for that is there's a classic problem in distributed programming, and that's you can set up lots of parallel processes that collaborate to do something. But what happens if any one of them goes wrong? At that stage, you want to make sure that everything dies that's involved. Every single process. You might have 15 processes all sort of spread out doing stuff. And if you want the invariant, if anyone dies, we all die. So that's what the link does. Just set the links up. It doesn't matter who starts. They'll all die. And it's an invariant. That's why we don't do defensive programming, actually. You know a file system on Unix? A process that opens a file and starts reading and writing to it. If it crashes, the operating system closes the file in a nice sort of way so that the next program that comes along can open that file. It's not like the file is broken forever because the process that was using it crashed. So real-time things all we do is we sort of assume they're going to work, program them as if they're going to work, and then set up some guys who monitor them. And if they fail, we put back these invariants, just kind of pick up the pieces and put them back together again. That's the failure detection. And yeah, we're pretty religious about fixing errors remotely. You can't fix your own errors. Okay, so if I fell over and had a heart attack and need open heart surgery, I'm not going to do it myself. Like, where's the knife? Some medics come in and sort of carry, and some other guy fixes me up when I'm dying and things like that. So we do that with processes. Think of these errors, they're like little ambulances that sort of run in and fix up things that go wrong. It gives you very nice separation of issues. You've got processes whose only job is to do stuff. Then you've got other processes whose only job is to repair what's gone wrong if the processes that do stuff fail. And then you've got managers whose their only job is to manage people and start and stop them and do things. So it makes it actually pretty nice. And yeah, here's one or two little extra things that we bunged in here. Spawn link, that spawn created a process. Spawn link creates a process with a link so that if the process dies, you get a message. If you don't do that statement there, your process will die if the other process dies. But if you do put that statement in, you get an error message, which you can receive just like anything else. And we've got some live code upgrade. This actually, it's quite convenient to, this actually means something different. If you call bar, and you've got a module with bar in here, and the module's called foo, it'll always call that no matter what happens. But if you say foo::bar, and you upgrade the code for bar at the same time as you're running it, then this will hop into the new version of the module and carry on in the new version, and the old one will carry on in the old version. So actually, you can now, without changing the names of any of your modules, you can actually have two completely logically different versions running at the same time. They've all got the same names. And this old version is, well, actually it's a mistake in the language. When Erlang was designed, we didn't have much memory. I mean, that was 86, something like that. Today, I would do it different. Today, I would have multiple versions with the same namespace and garbage collect code. You know, if you're performing a computation, I mean, suppose we spawn 500 processes to do the same thing, and some of them are long-lived. Some of them might last for months. Others are short-lived, and then we go again in a cycle and do it again. We might change the code while we're doing it. We don't really want to change the code in the things at arbitrary points in time. We maybe want them to run to completion even though the code is old until we get to the next time they restart and then give them new code the next time they start. But we don't want to kill off the old ones who are using the old code just because we've changed to new code. So it's like having regular modules or classes or namespaces, but thinking you can actually run the old code and the new code at the same time. So imagine Java, you've got a class called something or other, and it's in the JVM, and you change all the definitions and just bung it in again, and bung it in again, and bung it. But the old ones that are still running the old code, they're still running the old code, and the new ones are running the new code, and it's all hunky-dory and works fine. And then we got stuff for stable storage. Manesia is a real-time database that has the property that you can configure it for multiple nodes, and it replicates in RAM and does things like that. It's all very nice. Oh, I'm running out of time. Let's see. So once you've done all this, once you're thinking in terms of isolation, the isolation thing forces you, when you design your system, to break it up into separated components. So it's kind of rather nice, you see. In order to make things fault-tolerant, you have to design it so that the components are isolated. And so you got your scalability for free. You didn't have to think about how to scale it because you've designed it correctly. Hey, that's great, it comes for free. But it's the other way around. Suppose another guy is going along and says, oh, I want to make a scalable system. So you design it in isolated components. Ooh, it's become fault-tolerant for free. Ooh. Well, hang on, wait a moment. If they're isolated and it's scalable, maybe we can run it on a multi-core. Ooh, yeah, no, it should go faster, yeah. So when the multi-cores came, this is probably why Erlang took off back 2004. The multi-cores started coming along. We ran a lot of programs on multi-cores. They just went faster. We didn't have to do anything to them at all. Just bunged them on the multi-cores. They went faster. So the goal was, sort of, if you go to quad-core, take your old program, bung it on the quad-core, it should go 4 times faster, we hope. Some programs do, actually. Our goal is to get like 75% of the number of CPUs in speed up. So if you've got 12 cores, we hope to get like a factor 8 speed up without doing anything. Of course, it depends how you've written your programs. If you've written them with one big process, you get no gain. But if you've written them with lots of little processes, you should get these gains. It's very unusual that you don't get any gain at all. And then as you start scaling up, funny things can happen. I'm going to show you a little bit about that in a while. So actually, it's kind of fun because everybody else is saying, how do we take a sequential program and run it and parallelize it so we can run it on a multi-core? And the Erlang people are saying, well, it already runs on a multi-core. How do we find bottlenecks? So we're looking for bottlenecks now. We've already figured out how to. When you write your program, every time you write spawn in your program, you're saying, oh, well, I've decided that can be done in a parallel process. And then you just bung it on a multi-core, it goes faster. We're looking for the bottlenecks now, and I'll show you that, because that's quite fun. So what do we got? In all of this, we've got, this is a kind of summary, we've got lightweight processes, fast message passing, total separation between processes. Stuff. Very nice stuff, actually. More of this is kind of what you would associate with operating systems, rather than, you see, Erlang's not really, you don't need an operating system, really. The operating system just sort of, when Erlang starts, it just says to the operating system, give me a heck of a lot of memory, please. And that's about the only monitor call it makes. And then it does everything itself. I mean, it schedules itself, and it doesn't use the operating system scheduler or anything like that. So it's awfully big, the stuff. Let's have a look. And we've got all this stuff. I'm going to hop over a bit of this. It's taking too long. Yeah, I've run onto a few little projects just to show it's not just Ericsson that uses Erlang. CouchDB was one of the first projects that kind of spread a little bit and quite a lot of people used. And then React, there's some React people here, so go and ask them about React. They'll tell you how wonderful it is. Chef 11, in case you don't know, this is the thing that it's a management system that monitors machines. So I think the Chef 11 servers are written in Erlang now. It's client-server architecture. Servers written in Erlang, clients are written in Ruby. And you monitor loads of machines. So one Erlang node there can monitor about, I don't know, 100,000 machines or something like that. So that's being rolled into Facebook. So Erlang will be controlling every single Facebook node on the planet. It's quite nice because it's good for that kind of thing. It's good for monitoring thousands of machines. It's good for having, you can get about 3-5 million sockets running on one reasonably sized machine in Erlang. Mocky Web, that was running, Facebook Chat was run using that for a while. It's not using it anymore. It's been replaced by I think, a web server called Cowboy in Erlang. Scalaris was a distributed peer-to-peer thing. Actually, they implemented the Wikipedia, not the real Wikipedia. The research group in Germany won the prize for the best scalable system. They implemented the entire Wikipedia using something like 1/10 of the number of machines that the Wiki really uses, but it was written in Erlang. But they never managed to sell it into Wiki, I think. This is quite interesting, eJabberD. It's an XMPP server. It's the most widely used XMPP server in the world. And it was actually that code that was modified to form Mocky Web and a lot of things. And it's actually WhatsApp, the WhatsApp application. This is a mobile thing which switches, I think they were saying 10 billion messages a day or something. That was actually based on the XMPP code by a student who'd learned Erlang, and they built this thing. I think they valued it. I reckon they'll sell themselves to Google or Facebook for a few $1 billion. So, I mean, that's what you can do if you just learn Erlang as a student and just write. I mean, nobody's interested in commercial, in sort of programming now, but you make money by building applications that people want to use. RabbitMQ. This is the first compliant implementation of the advanced message queue protocol. RabbitMQ did this, and then they were acquired by I can't remember the name of the company. It was then acquired by VMware. So the VMware distributed system is actually using Erlang sort of hidden in the bottom layer using RabbitMQ to manage them. It's quite fun. It's a load of companies. Ericsson's pretty big in Erlang, using it a lot. Basho, TLF, Klarna. These are all Swedish companies. You probably don't know much about them, but I mean, at the current rate of expansion, this is going to be bigger than Google in about 6 years' time. And it's a financial company, and it's grown. It's the first pure Erlang company that's valued over $1 billion, and it's got something like 800 employees or something in 5 years, and it's going crazily good. And WhatsApp TLF is managing a lot of Cisco routers and things. There's a load of books. This is actually a really good write. I don't know if it's a good read, but it was quite fun writing it. It's the second edition of the Erlang book. So it's got all the new things in Erlang that none of the other books have got in yet. Right. So a couple of slides on some fun stuff. What's in the future? I'm going to show you two slides. Well, I think this is kind of Elixir is really fun. It's like son of Erlang or daughter of Erlang. It's a language that uses the same. I said Erlang was three things: a language, it's a set of libraries, and it's a virtual machine. So Elixir is the same virtual machine. It runs on top of the Erlang virtual machine. So all these nice things I talked about, all these things about links, all these things about process isolation, all of that is in the Erlang virtual machine. It's not anything in Erlang itself, it's in the virtual machine. So Elixir gets all that stuff. And it's got a Ruby-like syntax. And it's got some fancy metaprogramming in that you can't do in Erlang. So it's actually very nice. It's really cool. And it's taking place in a completely different way than Erlang. See, when Erlang was developed, that was before the World Wide Web. We were talking about this in 1985, 1986, Robert Virding and I and Mike, and I mean, the number of people who could take part in this debate about how a programming language should be was limited to the number of people in the coffee room. You know, we talked about it every day. Oh, I should do it this way. No, I do it that way. But this debate is taking place on the net. So you know, there's a mailing list there. I'm talking to Josef Alin and mailing him and saying, why don't you do this? And a lot of people are contributing ideas. People who've never met, you know, people in the Soviet Union, people in America. And it's Erlang, I think the gap between the first book and Erlang was something like 14 years. Right, the gap here is about a year, because Dave Thomas who's the guy who introduced Ruby to everybody. He's written this Programming Elixir, and the first draft's out as a beta book. You can buy it and read it now. And there's an O'Reilly book that's out. I've read both the drafts. And so the documentation, the books which you need, are being co-developed with the language. We've never seen this before. There's always been this long gap. Even Ruby was kind of developed, and then Dave wrote the books. So I think this synergy effect is going to be very good. And I think it's a very exciting experiment, because the OTP people are really keen on this, and I'm very keen on it, because we can combine kind of youthful enthusiasm with sort of this old-style engineering practice. We know there's a lot of engineering. There's probably hundreds and hundreds of man-years of work in the virtual machine and in the libraries, and we can just sort of glue them all together. So this is very exciting. The other stuff, this is cool. I'm just going to show you a little video, if I can make it work. This is Concurrency. Now, somebody earlier asked about, wait a minute, I've got to go to, somebody asked about, somebody said, you know, can you find bottlenecks and things like that? So you remember that picture I showed with lots of little dots? They say, how do we understand a system like this? Well, let's see if this works. Oh, where's my thing to press? Oh, heck. Oh, there. Let's hope this works. What? Shouldn't be so violent. There. Any sound, please? No?
Thank you, Joe, and hello, Lambda Jam. My name is Alex Canaris, and I'm the CEO of Concurrency Corporation. Today, I'd like to show you a few of the tools we've been working on for Erlang performance. Our flagship product is a real-time visual profiler. It consists of two parts: a tracer, which hooks into the Erlang virtual machine, and a set of HTML5 visualizations. Installation is easy. Simply add it to your rebar config, and away you go. The code here is for a website that generates Mandelbrot sets. It's a simple program written in the excellent Chicago Boss framework. Now let's see this in action. Here it is running live in the Concurrency visualization tools. Every circle represents an Erlang process. The size of the circle is proportional to the amount of computation. Lines represent communication patterns, and the yellow dots represent the actual messages being sent. So far, it's pretty stable, not much happening. Let's add some load to it and see what happens. As we're adding load, you can see hotspots develop as the program struggles to keep up. The beauty of these visualizations is that it makes it super easy to see exactly where your program has the bottlenecks. Here we're zooming in on the bottleneck in this particular program. The bottleneck that we found is a common one in Erlang, where many worker processes communicate with a central singleton process, and that singleton process becomes a choke point for scalability. To figure out what it is, simply put your mouse over it, and you'll be told the module name, function, and process ID of the offending bottleneck. Well, that's it for our whirlwind demo of a real-time visual profiler. We hope you found it interesting and useful, and look forward to your feedback. Thank you all very much.
So that's what you can see when, you know, it's like a gas. I'm wondering if it's going to obey Boltzmann's equations or something, or Boyle's law. PV is RT. You know, if you compress this, you know, the processes get hotter and they sort of buzz around faster, and the CPU will get warmer. And I want to see if we get to like statistical mechanics for understanding how these work. Because I think we need to go from this. You know, I showed you this picture. We need to go from this world where we think that we program using single processes, to this world where we program with sort of thousands and thousands or millions of processes that are communicating with each other. So I think if you take away a message from this talk, I think that's what we need to be thinking about. It's not how single processes behave, it's how aggregates of millions of processes behave and how to build systems out of that. So I think that's about where I get to. Yeah. Thank you.